Welcome to AI Talks. I'm Nate and this is Seth. And who are we going to be talking to today, Seth?
Today we're talking to Josh Bloom. Josh is the VP of Data and Analytics at GE Digital, and he's a full astronomy professor at UC Berkeley. Previously, he was the co-founder and CTO of a company called Wise.io, which got acquired by GE Digital in 2016.
Okay, that sounds really cool. Let's get into it.
All right, welcome everybody. We're here at a WeWork in San Francisco, and we're here with Josh Bloom, the VP of Data and Analytics at GE Digital. Welcome to AI Talks, Josh.
Thanks for having me.
Of course.
So the first question we like to ask everybody now that they're here is, how did you get to where you are?
Well, obviously, long story. Nothing is ever completely linear. I started off as a physicist. I did basically all of my degrees in astronomy and astrophysics. And over the years, got very interested in what you might call the informatics of understanding how we do inference and prediction on the types of objects that I was interested in the sky. And as that was unfolding, I started getting interested in machine learning and wound up building up a group at UC Berkeley of statisticians and computer scientists and engineers. And together we started building these large-scale systems that could do inference kind of on the fly. And so from there, we started branching out, started thinking about where could we apply machine learning more broadly. And that was the genesis of my company called Wise.io. From there, after doing that for 4 years, and we can talk about that, of course, we sold the company to GE Digital. And that's the short story of why we're here and how I got here.
So, I mean, a lot of the viewers that we have are probably engineers that are interested in getting into data science.
Yeah.
And they're probably really interested in what's the difference between doing data science and doing data science in production, and how engineering is involved in both.
Yeah, so I can speak to that. And some of it comes, from the battle scars of having tried to do this and failed in all these really interesting ways, and then getting to where we got and where we are now. Now it feels very natural how we've sort of architected our solution and what implications that also has for the people that we hire and what we ask of them to know. Happy to talk about that. But I've seen this not just with our own experiences in our own startup, and then also at GE Digital. We've also seen it in large companies that you would expect to be really good at this stuff. So there's a very large internet media streaming provider in the Bay Area. Yeah, I don't remember their name actually. It escapes me. And we met with, at the time, as we were an independent startup. And we were at the time, by the way, not selling applications as we wound up getting to, but selling more sort of toolkits and components of platforms early on. We were sort of thinking of them as a great company for us to sell to. They had sort of an AI ML research team that would take an SSI's version or an SSI's scale of the data that this company had to work with. They'd build up new algorithms, find that things worked really well. They've probably coded in C++ or Python. And then they told us they literally would take the whole code base and walk across the quad and teach the engineers how to implement it in Java, which would then take another 6 months, and it opens yourself up to all these other problems. I think what's happened since then, that was maybe eight years ago or so, is kind of a recognition that if you're working in a sandbox environment, you need to work with tools and approaches that at least have a shot of immediately being able to drop into a production environment. So, this is happening in the context of TensorFlow. There's the ability to serve TensorFlow models now that come sort of batteries included. Companies like Amazon, AWS are building things like SageMaker, which allow people to build, fairly sophisticated machine learning workflows in a Jupyter notebook, and then deploy them so that they become sort of APIs that are scalable behind the scenes. Cool. So this is now becoming more and more possible, but it's taken the community as a whole, I think, a long time to recognize that if you work in R or if you work in Python or you work in MATLAB and you get a good answer out of the initial look at the data, that's not the end of where data science is, right? Data science, in a lot of cases, winds up needing to evolve and move into a production environment where it has, real-world implications on a minute-by-minute basis or a millisecond-by-millisecond basis. And typically, in the end, it's a person or a group of people that are going to be on the result of, or be on the receiving end of the result of the predictions that are made by these systems.
Yeah. Connected to that, I know you wrote about some of these themes in your article, cost-effective AI. Do you want to sort of expand on what you were just talking about and talk about how it relates to cost-effective AI and maybe even transitioning into sort of what you're building at GE?
Sure. I mean, I think the point of departure for our thinking on this, or at least the group that made this most clear in our minds, was a group that came out of Google, a paper by D. Scully on what is called, I think, the Machine Learning is a High-Interest Credit Card of Technical Debt paper, which is definitely required reading for your audience. And there's no equations in it. I think it's 20 pages or so, but it's a whole list and litany of the problems that you get when you start thinking about building machine learning into software systems in a way that we don't often learn when we're learning computer science. In the university setting. In particular, this idea that you can have composable parts and you just sort of bolt them together, and that if I agree upon an API from part A and part B is going to be consuming that if I can test that on in an offline system, it's going to also guarantee to be working in a production system. Yeah. That whole abstraction boundary is completely eroded. So that paper speaks really well to that. And then Leon Bateau also had a very nice speech about that at ICML a number of years back about the challenges of systems engineering when it comes to machine learning.
Can I ask you? I want you to take a stand on a fundamental issue that I believe is sort of in the community today.
Okay.
And that is TensorFlow versus PyTorch. So I know some people that are in the academic research community, and a lot of them prefer PyTorch because it's flexible, right? It's very easy to iterate on, but it doesn't have a lot of good serving systems. Versus TensorFlow, really robust to serve, really fast, but it's sort of a little bit crusty to sort of work with.
But why aren't you asking me about Chainer or MXNet or Cafe 2 or Cafe 1? I mean, that's my answer to you is. This is it's not quite fair to say this because these are really important flavors, but these are flavors of the month. I think what you're seeing, which is extremely healthy for the academic world and for the business world, is this sort of competition in the platforms war, right? And I don't have a strong opinion for that in the same way that if you're given a bunch of data and you're asked to do inference on that. Are you a Bayesian or are you a frequentist, right? I mean, at some point, the question comes down to what is the question you're trying to answer? What are you trying to optimize for?
Yes.
And is the tool that you have in front of you that thing? If you just need kind of off-the-shelf, let's do some ImageNet, and we have a whole bunch of pre-trained layers, and we've got a slightly new problem, and we just need to do some transfer learning. Why not just use Keras? I mean, why not use some abstraction layer on top of the underlying, compute layer? So I don't have a strong opinion on that, and I think people that are fighting that war, it's a good thing for most of us. I don't really have a horse in that race. In the end, I think the ones that are going to win, and this is sort of an opinion that I hold reasonably strongly, are going to be the ones that figure out a way to couple the platform that's being built to the community that's using it, to the underlying actual sort of hardware that's going to be running it, to the domain questions that are being asked on that. And so in some sense, the platforms that'll win will be the ones that are more capable at addressing all the vertical issues. Right, so if you are Google and you're running, image search at scale, you are going to have a very strong opinion about which of the different components of that system are going to work for you. If you're Facebook, you're going to have another one. If you're building machine learning models that are going to be on a mobile phone, and you need to push them in a mobile phone and need to be this small, not this big, then you're going to come up with a different answer, and there it may be Cafe 2.
Right. Interesting. So, for our viewers that are sort of learning data science, and a lot of people, go to, say, Kaggle, and they take a data set and they run a bunch of models on it, and they try to just get the model with the highest accuracy.
Yeah.
And I think what you're suggesting is, if you think about the business value that you actually end up adding when you actually use these models, accuracy is not the only thing, right? You should think about, can it work in a production system? Can it scale, et cetera? So what kinds of sort of tools or resources should people be looking at that are trying to learn data science and learn how to become valuable data scientists, as opposed to just doing the thing people usually do, which is find some interesting data and try to build the best model on it?
Yeah, I mean, first of all, I think Kaggle's been has served an amazing role in the burgeoning field of data science by helping people understand the types of problems that are being asked, presenting them with real-world data. But you're right, one of the challenges is with Kaggle as it lives now, and although I think it is already starting to change, is that you win if you optimize a metric. Now the good thing is if you win and you optimize a metric, it's not that hard to then say, well, let's make that metric the total time it takes to learn, or the total time it takes to predict, subject to some other metric which is related to accuracy. I think what people are starting to recognize, given the quality of machine learning models in some domains like NLP, like in the image space, is that very good, accurate models are really table stakes at this point. And the difference between a 99.9% accurate model and a 99.8% accurate model in a real-world environment probably is not that much, right? This gets back to your original question, which we skirted around what are you trying to optimize for? And in the end, if you're trying to optimize for your time to value in a business sense, or in an academic sense, your time to get a new discovery, generally those epsilon differences in accuracy don't matter. And then what does matter is your ability to rapidly iterate and build those models quickly, because it's the carbon power from ourselves that's the most expensive, not the silicon power. It could be your ability to deploy a model that's actually interpretable, so people can actually understand it. It may be simple things like, I only have access to these sorts of machines, and there's these RAM restrictions where maybe I could get 1% more accurate models, but it would blow up my RAM and I'd actually never finish building this model. So there's all these other axes of consideration, and in the end, yes, you could build a metric over all of those and optimize on that one metric. I've sort of argued in the past that metric is cost. And that's including like opportunity costs of not working on something else. But anyway, I think what Kaggle has the opportunity to do now is start helping people recognize that the thing that's most important isn't just accuracy. And you've noted that, and I think as your audience starts looking at different tools, one of the grand challenges is obviously accuracy is something you can measure. There's very clear methodologies for holding out validation data. You know how well you're going to do on that sort of data if that's applied later on. But can you actually implement it in a real-world environment? Is in some sense the only way you answer it is by doing it. And unfortunately, maybe for your audience, is that this is not I can do it on a textbook, I can run Kaggle on my own, and now I'm a data scientist. I think the challenge that everyone is going to now have to face is, how do I actually get enough experience, by actually working in a real-world environment? And maybe the analogy is something like a blacksmith. Like, you can watch a blacksmith do their thing, you can read all the blacksmith books, but you're not a blacksmith. Right? You need apprenticeship. You need years and years of making lots and lots of mistakes and building up your own battle scars. Because in some sense, I think it's you are the sum of all the things you've done wrong, because then what's left is the stuff that you've got and you've done right.
Yeah.
Via negativa.
That's a thing? One comment I want to make is, so you mentioned that human power, carbon power, is more expensive than silicon power. But carbon power can be enhanced with coffee. So isn't coffee really the most expensive thing?
We could stick that into our metric, yeah.
Yeah, right, there you go.
One of the great stories I've sort of heard about this is that a bank was optimizing for fraud detection in loans or something like that. I think it was default detection in loans. They were trying to figure out which loans they gave would default and which loans they gave would not default. And their data scientist there was clever, and they said, do we actually care about default or not, or do we care about the amount of money, the expected amount of money that these loans would return? And I think that like improved the amount of money that the bank made by like 10% or something like that. And so it's kind of like common sense. This is not. There was no magic. There was no like magic formula. It's not like learning like cross entropy or anything like that. It was just.
But that's one of the keys of why data science may be different than what old school analysts might have been. It's the ability to connect the business question in a deep way to the math on the other side, right? And in the end, all these are sort of labels, so it doesn't really matter what people used to be called in the past and what they're called now. And plenty of people have said data science is too general of a term. But that's why understanding, what you actually are trying to optimize for. Once you start understanding that deeply, then you can actually do it. And then you can start leveraging all the tools of gradient descent to get to the optimization metric that you actually care about.
So getting a little more sort of concrete, you mentioned NLP as one of the areas where there's been a lot of advances and new applications of NLP to business. So let's talk about WISE, and let's talk about what it was, what the business problem was, and what you built, and what you see in general as like NLP how NLP is being applied, in business. Not so much what's going on in the cutting edge of research, but like what are the things that add most value to companies? Yeah.
So the application suite that we wound up building at Wise.io was in customer support. And that product suite now lives on in a company that GE basically spun out and has an equity stake in called Answer IQ. So the product suite that we built over the years is still in the market, and some of our original customers are still with this new company. And what our team does is basically provide the machine learning backend to all the middleware and front end software that this company is building and developing. So the idea here is that the code base basically interacts with Salesforce and Zendesk. From a subscription kind of model perspective, what we're doing is looking at tickets as they come in. These are support tickets from companies like Groupon and Twilio. And instead of having people answer a lot of these, what the system does, it reads these tickets, makes some decisions essentially about who this should go to, which sort of triage team it should go to. Is this level 1, not that important? Is this sort of on fire, go to the CEO? And then also make some recommendations about how to actually solve the ticket. What we wound up finding over time is that where our product suite worked best was with reasonably well-established customer support teams that were big and growing, because they were feeling the pain of the inability to actually hire people fast enough. So you're looking at companies like Thumbtack, which are growing tremendously fast and needing to onboard very high quality customer support agents. This was an ability to sort of give them a leg up and sort of supercharge the agents that they already had. And in working with companies that had clients where a lot of the answers could be, or a lot of problems could be solved with one answer. So rather than a back and forth, some you can imagine some tickets take months to actually resolve. It's a very complex technical issue. But if this is like a password reset problem, why do you need your precious carbon power to be applied to read something, go, oh, this is password reset, here's a little macro template to respond. So the way that we wound up pitching it, and it's still pitched, is that this is sort of a supercharging agent that sits in the background and answers tickets when it can, and it can do them automatically. And when it's not confident in those answers, instead, sort of, we get some real estate on the support desk agent screen and sort of make some recommendations for how they should respond. And then we built the feedback loops in, importantly, back to the discussion about systems, so that when an agent would take our response, we would give ourselves sort of a thumbs up, and when they didn't, we'd implicitly say, well, we had the wrong response. So in the end, this is an application suite for non-technical buyers. non-technical users. And machine learning is maybe a foot in the door to get people thinking about it, but in the end, it actually has to work. And back to the question about accuracy, it has to be good enough that somebody can see a value proposition in, giving you part of their software budget. What was important about what we built, and obviously, the importance of being closely connected to customers and being part of the, iterative feedback loops that you get in product cycles by hearing the voice of a customer. But from a technical perspective, what was important is a recognition that you can build machine learning models using natural language processing for individual customers without having to cross customer boundaries of having to aggregate all customer data and build some global model and just have it work. What we wound up realizing in some sense is that the language of customer support, both on the company side and on the client side, is very specific to that product. And as we went through and started working with different NLP packages and different approaches, we wound up finding, surprise, surprise, that bag of words worked incredibly well.
That's what I was going to ask. Right. Okay, cool.
Exactly. Yeah.
Great.
This is also in the context of WordEvac and Glove and all these really sort of interesting, sophisticated models, and now there's entire language models. What we're finding is that good old bag of words and TF-IDF and all the old school stuff went up working good enough for us to build this product and get in the hands of people that actually found value with it. But what you also wind up realizing, and back to this D. Scully paper from Google, is that the machine learning part of the application that we built was a tiny fraction of what was actually in the market.
Just want to ask you this. Yeah.
So it's all the cybersecurity, it's all the database interactions, it's the UI in the front end, it's adhering to the Zendesk and the Salesforce APIs. It's basically how do you onboard a customer without needing new data science work, and that was a critical moment for us to arrive at, where we would have a technical set of sales calls with customers. And we basically just say, well, if you're ready to go, just OAuth into this system. Our system is going to pull over all the data. Models get built automatically, and the out-of-the-box models tended to be good enough for most companies that we could have them up and running in less than a day with more or less no data science time. And so we wanted to get to the point, and I think this is maybe also important for your audience to think about, is not how can I use the coolest, best machine learning that I just read about on Hacker News, but how can I use the most Joe Vanilla stuff that exists, that I know is going to scale well, that people have been using for a long time, and build a product around that people actually want. And how do I not have to use expensive sort of PhD level computer science and stats labor to onboard a new customer? Right. Now, we often would try experiments where we'd see, what if we had an aggregation of lots of data beyond just an individual customer, and let's say we augmented that with a Wikipedia crawl, and it just didn't do that much better, but the computational cost of doing that was so much higher that we just said it's just not worth it for us to keep going down that path.
Makes perfect sense.
Okay, so I've got one hard-hitting question that I want to ask on sort of the tail of this. So in a way, Wise.io kind of eliminates a data scientist's job, sort of. It used to be that a data scientist would work at a company and they would have to go, and maybe there would be this task of doing this automation task that they would need to solve, and they would spend time, work a year on it and sort of push it out, right? And there's a ton of other things that are trying to do this. Google AutoML is sort of one of the bigger examples. There's a ton of pre-trained models that are out there. Are we going to have jobs as data scientists in the next 5 years is the question.
Well, that's a hard one to answer, but what I will say is I don't think we were taking away data science jobs.
Okay.
Right. In fact, when we would interact with a data science team on the other side, they'd say, we know this is going to work.
Yeah.
Right. We've done our little exercise. We did a hack day on this. We know it's going to happen, but we don't want to build this. Right, a data scientist, and I think the definition that you may be operating on is one who is, building models, doing some inference, figuring out, accuracy, and then moving on. That's a very important role. But in the end, you still need something more than that kind of role to build an entire application and have it work at scale. The other thing is that a data scientist and maybe even data science team that would have not hired us, not used our code, but instead, or our application, instead try to build it themselves. And the build buy decisions happening all the time. And some of these very large scale companies, even for things like customer support and automating that, even though that's not their core competency, still have enough wherewithal, enough capital, and enough smarts to be able to build these systems themselves. But what they don't get is access to all the different ways in which customer support happens. And when we built that application, you take it to market with your first customer who crosses the chasm and says, let's do it, and you build everything that makes sense for their environment. And then even if you're still working in Zendesk, and even if it's the same industry as customer number one, customer number two is going to show you that you didn't really understand things as well as you did, and you start to need to generalize. And so I think the short of it is that there's always going to be a role for a data scientist to look at problems afresh and figure out new directions of where you might go from a research perspective, where there might be value that's being left on the table. But I think we're always going to have to make the build buy decision as a company. Do I want to throw my precious data science resources at something which is on the ancillary parts of my business, or do I want to throw them into the core of what differentiates me from my competitors? And so I think what's going to happen is over time, we're going to be, as independent companies, we'll be just buying applications that already have AI embedded in them and have the good data science tools embedded in them that work sort of seamlessly behind the scenes. And we're still going to invest in AI researchers and machine learning engineers to build systems that help us with our core competency.
That makes sense. So
it puts my heart to rest.
It puts Nate's heart to rest. Wonderful, wonderful. Completely to rest, like on everything.
If we had another hour, I could talk much more about it.
Okay, cool. I think that's actually a really good transition point. So when I go to conferences, or so by the way, Nate and I met at ODSC West in November 2017, and Josh and I met at ODSC East in May of 2018. So I go to these conferences, and I see a lot of people talking about data science platforms that they're building. Right. And it seems like this is a very broad term that's used to describe a lot of different things. I know, like, Wise, in some sense, you described it as an application, but in some sense it's a platform. I know you're building some platforms at GE. So talk about that. Like, what do you see as the value that data science platforms add, and sort of what, I know it's a vaguely defined term, but what are they for our viewers? And maybe transition into what you're building at GE.
Yeah, so I think of platforms in general as horizontal, scalable systems that enable people to leverage things down the stack. So hardware, bare metal stuff. At the bottom end, and then above that to build applications that are specific to their domain for their vertical. And so you could consider an operating system as a platform, because then I can drop in applications that can do games, they can do spreadsheets, and they talk to the underlying hardware of my laptop. You could think of a Salesforce as a platform for the ability for people to put data in and do things that are very custom to one's own company, but where there's some guardrails of you can't do everything in the world. You're not going to do quantum computing on the Salesforce.com platform, and you're not going to solve traveling salesmen's problems, right? But you can help your marketers do ad retargeting better, right? So there is some opinions. It's not fully horizontal. There's some opinions, but it actually can do quite a lot of things. So this is kind of as opposed to the vertical view of a system, which may leverage a series of platforms. It's going to be, Python sitting on top of Amazon and using all of its different services, and then using a database that's maybe built by some open source third party, using a web framework, which you could consider a platform as well, and tying all those things together to do something very specific for that application. What Wise did as an independent company was basically build up an application layer that allowed us to stamp out new machine learning applications quickly without having to rebuild code from the scratch and make new decisions over and over again, but with a very verticalized focus. So all done in service of us being able to take a new product or a new capability to market quickly. That is, I think, what GE Digital found most exciting about our tech stack, is not that we were working in customer support and we're good at NLP, but with 98% of the same code, we're able to do a real deep learning project, not as a one-off, but as an actual application. And so seeing us as an enabling tool to build these out and embed them into the sorts of products that GE is already selling and using themselves was, I think, a really big selling point for them in what we had going. You asked me about where do these fit and how do we use them. I think platforms are absolutely essential, but I wouldn't recommend anybody in the startup space in particular to try to build one of those, right? Because to be a successful platform, back to some of our earlier conversations about PyTorch versus TensorFlow, you need to be a major company backing a major platform if you're going to win. And in the end, it's not going to be 12 platforms that win. There'll be only a few. And it may be that they only win for a couple of years, and then a new one comes along and bests them out, right? PyTorch, in some sense, came out of nowhere and just overtook what it seemed like TensorFlow was going to be the inevitable platform winner for deep learning. So I think it's important to understand the landscape of what platforms exist, and whether you're going to build one yourself, which would require a tremendous amount of energy, and you'd have to have a really good reason to do that, or use somebody else's out of the box, or use somebody else's but add some modules to that to give you sort of a specialized leg up. That's really going to be very context dependent. So I don't have a strong opinion on exactly how one goes about that.
I see. Cool. Getting back to Nate's question from before, I think one reason I always think that sort of companies that build tools that make it easier to do data science work, that make it so that one person can do a job that 4 people would do before, that actually increases the number of data scientists long term. I always think about this. Imagine if sklearn hadn't been built.
Sure.
So you had to do cross-validation from scratch. You had to do all these models from scratch. Do you think there would be more data scientists or fewer?
Right, and this is the explosion in the number of people learning deep learning is probably because it's so easy now. You don't have to go in CUDA and write gradient descent yourself.
Exactly. So when you build these tools for GE, I imagine that makes it so GE can hire more data scientists.
Absolutely.
Fewer, right?
That's right. And it's about time to value. It's how quickly can we bring AI-infused products to market, either for our own consumption within the vast GE ecosystem. And we've got partners in the oil and gas sector, in aviation, in power. We're working with renewables. So GE is this huge sort of customer base in and of itself. And the things that makes GE great is our ability to have a special relationship with the various different components of the company, and not have to have this sort of hands-off, commercial relationship. We're part of the same family. We're under the same, sort of sets of regulations around data, et cetera. So it makes it easy for us to be able to take what we built as an independent company, grow that out, expand essentially our platform, and infuse it directly into the products that GE is using itself. And the next stage of where we're heading is now starting to infuse it into the products that GE is selling to third-party external companies.
So, out of curiosity, I think a lot of us know where machine learning products sit in consumer side, right? You see them in the Photos app, you see them in search and all this stuff. Where do they exist in the industrial side?
Right.
Well, this is what's so great about being at GE is that this is all just beginning, right? So yes, you know about that because it's been around for 10 years. One of I think the fascinating aspects of the sort of industrial Internet of Things, IoT, and the types of equipment that GE builds, we sell, and then we service, is that these are physical systems, right? Unlike an NLP problem, how are you feeling about something? There is no actual ground truth to that, right? Or what's the best recommendation for you to buy next? You can do math and get an approximation of what you think might be the best, but there is no actual answer to that. But what's nice is that GE's been working and building these systems for a century, and we have a great sort of physical understanding of how they operate and what their potential failure modes are going to be. And so without needing machine learning and advanced statistics, one can get a very long way with physical models of these, right? Simulations, or you understand that if the temperature goes like this, then the pressure is going to go like this because you're conserving, pressure times time, whatever it is, right? And so that, in some senses, held back the industry from a need to adopt in the way that the consumer world needed it, because that was the way you got sort of the virtuous cycles and got bigger and better and faster than your customers, is to get the data network effects. We didn't really need that as an industry. And I'm not even just talking about GE, I'm just talking about sort of the heavy industrial world. We didn't need that. Now, as we're starting to see the value of it, now we're starting to just sort of find all this low-hanging fruit where it becomes really obvious that you need machine learning, or at least that machine learning could help a whole lot. And so what we've done in our first year and a half in the company is survey the broad landscape of the company to understand where are the workflows where people are making decisions on machines or operations that need to happen on machines, and where can we actually infuse machine learning into that. So it rhymes a little bit with customer support in the sense that we're trying to not do this in a unsupervised context. We're not doing it with a reinforcement learning lens. We're just doing it with a supervised lens of, is this jet engine in need of coming off the airplane? Yes or no?
Yeah.
Right? And GE has hundreds of people who are the world's experts in looking at data coming off of jet engines and making some decisions about when do we need to set up a new service for that engine, or when is there a potential real bad problem we need to do something more quickly. Instead, what we're doing now, and this is something we've already taken to market and we've been public about, is we've injected AI into this to make those analysts in the monitoring and diagnostic centers essentially supercharged, where we're taking away all the easy stuff of this alert that just came up is a false alert, don't look at it. This is a real big burning problem. We need to have a bunch of people looking at it and thinking about it. Those are kind of the easy ones. And then it allows the analysts to look at the gray areas, and it allows them to have the time to look at those gray areas. So a big part of what we've tried to do is, like in the aviation use case, find those places where enhancing workflows with AI is going to be tremendously valuable. But as you can imagine, this is not like if I serve you the wrong ad, who cares? This is if I miss something important, that's a big deal.
The jet engine falls off a plane.
It generally won't be that bad, but it may be that we missed an opportunity to service a jet engine sooner rather than later. Or there's the kind of false positives as well. You wind up taking an engine off a plane unnecessarily because you think there's a problem. That's about $200,000 every time you do that. So the stakes are very high, and what's exciting about it is it's there are lots of opportunities like that. B, we're not taking people out of the loop. We're just sort of giving them better suggestions and taking the easy stuff off the table. So in the end, there's still the person in the loop that the industry has come to expect. But C, because the value of the problems are so unbelievably high. Sort of typical numbers in the oil and gas industry, for instance, if you unlock 1% efficiency, you're talking about tens of billions of dollars a year. It's just mind-blowing how much you could do if you get slightly better. Yeah. And so that has attracted a lot of people from the consumer world, the data science community, to start asking, how can we maybe work with you? And wait a second, so you're talking about every jet engine has a terabyte of data per flight?
Really?
Yeah, there's 50,000 flights a day that GE monitors.
Are those sensors? Is that what that is? Just sensors giving?
Yeah. Every engine, terabyte of data.
Terabyte of data per flight.
Yeah, 50,000 flights a day.
And
so you've got the number of airplanes circling right here in the Bay Area now is like an entire Twitter day of data. So the point is that there's a tremendous amount of data, and it looks different than the data that we've all grown up with in the consumer world, where it's like the Amazon recommendation engines, it's the Twitter sentiments, right? There's a whole bunch of classic problems that have now been worked on, done extremely well, and now people are kind of squeezing blood from a stone, like an ad targeting thing, for instance. You're now down to not accuracy, you're now down to how fast can you do it.
Yeah, right. So yeah, I'm curious to get more into that. So like you're looking at these sensors and trying to figure out, is there something abnormal? Is it kind of anomaly detection, time series? What kind of?
So the data is fundamentally time series in a large class of the problems that we work on. There's another class of problems we work on, which is image-based, right? And these images don't look like dogs and cats and F-16s, and so you can't use a ResNet, you can't use a pre-trained image net and use all of that and just get a good answer really quickly. You have to delve extremely deeply into the physics of what's producing these images. So for instance, we have another application that we've built within the oil and gas space where we're looking at essentially ultrasonic images of the inside of pipes. Where these images are taken at the millimeter level, at the sub-second level, over hundreds of kilometers of pipe. And the traditional way of dealing with this problem has been to hire and train really good analysts to look at every image of this pipe. But it's not an image that you flash on a screen. It's a representation of the data, and then you have to click on something and go into it and click on it again. You go into all these different facets and dimensions. So it's a very iterative, interactive problem. The type of neural net that we had to build to deal with this data, which is sparse, noisy, every pipe is different, every robot sensor is different, is something that doesn't exist in the academic literature. It certainly has been informed by a lot of the work that people have done, but what you wind up realizing is that real-world problems don't look like benchmark problems.
Right.
And when somebody says they know machine learning and they haven't actually worked with, this is now really dirty data, right? It almost literally smells like oil. Like I hand you this like terabyte of data or 100 terabytes of data. It's the nastiest thing that you could possibly imagine.
Get all oily.
Yeah, exactly. Yeah, the bits just fall onto the ground.
So you mentioned jet engines, and you mentioned this oil and gas problem where you had to sort of build a custom neural net that was taking like noisy images, and I imagine that brought you back to astronomy a little bit, because I know in astronomy, right, you have these images of stars and you have to like denoise them. So I'm curious to get into the weeds on one of those problems and talk about like how did you build that neural net, right? Like, did you start with something open source, sort of off the shelf, and then do something more custom?
Yeah, that's right. So back to the discussion of the tech stack that we had built and this sort of platform, which we call the factory, which enables us to build out new applications. The sharp elbows that we have, and this also gets to how we organize our teams, is that the data science team, as they're called, has to basically live within the confines of a Docker image. And so they get to set up their own dependencies of what needs to be in there, but in the end, we need to be able to call that Docker container once it's instantiated and say, build me a model, and it needs to spit out a model, which typically is saved onto disk somewhere. Or you ask RESTfully, generally, from a microservices perspective, of this system, I need a prediction for this model. Here's some new data. Here's the data itself in a JSON packet, or here's a location on disk of where to go get it. It then needs to spit back a prediction really, really quickly. And so when we start off with a new problem, it's not let's start from scratch. It's, okay, we already have this notion of a data science Docker image. It's generally batteries included, but sometimes you need a new thing. So we were working with Keras with a TensorFlow backend, and we had gotten sort of one run of data from one pipe run of, say 50 kilometers. And you start looking at it and you wind up realizing, and this is something that's been said many times, most of the hard work is in the munging of the data and the cleaning of the data. Unlike when you pull the data from Salesforce where it's all, the schema, et cetera, this data all just comes over and it's effectively just raw buried. One of the things that I think I'm extremely excited about, and the team is as well at GE, is that GE Digital's focus is increasingly more on applications. And so we have an application called APM, which is sort of our marquee application, and that's for it's asset performance management. So GE is one of the leaders in basically letting people, upload their data of, let's say, a set of wind turbines and have a single single place where they're actually monitoring that and get dashboards to be able to ingest that data. What we're going to be doing over time is ingesting some AI into some of the processes that people use there. What's nice about that, though, is that it's leveraging this thing that GE's been building called Predix and its set of components to kind of pre-normalize that data. So even though there's a wind farm that's using these set of turbines and another wind farm that's using these set of turbines, from an application perspective, we're just hitting an API and getting back time series data. And yes, it could have different ranges on them, but at least I know it's time series data, right? And so there's opportunities, and this is where I think some of the greenfield is for GE, is to be able to build these applications, sell it to our customers, where we create the equivalent of a Salesforce ecosystem where people are going to be putting data in, it gets pre-normalized, because then that's where people like ourselves can build these advanced analytic tools on top of it.
Cool.
Yeah. Wow. This is something that spans cross-industry. In finance, in current tech, and as you're saying, in industry, getting, cleaning, munging, all of that data it's 60% of a data scientist's job, and it's their least favorite part.
Sure. Most data scientists is their least favorite part.
You kind of hit upon some of the most interesting problems, or at least identified some of the biggest distinctions that we have in the industrial space relative to the consumer space, and recognizing that the consumer space isn't just about, a pejorative say like, optimizing Twitter data. There's this whole other world of the industrial space where there's all this low-hanging fruit. That's what gets a lot of our data scientists out of bed. It's why what we do still feels impactful. And being able to work at a company like GE means you turn something on, you have a global impact. I mean, we have a dashboard in our office which shows us essentially the number of jet engines we touched today.
Right.
And when we do a new engine family, the whole goal is not to do new data science. It's to basically do a new config file that organizes the data science for that new engine family. What took us several months to integrate with all these different systems for one engine family and getting that all working, on the next engine family, we'll be able to do that in a couple of days. The next one after that, it's a couple of hours. Right. So being able to crank things up and just start seeing the global impact of what you do is in some sense what I think all data scientists really want to be able to do, and we get to do that here.
I'm very curious about this. It's something that sort of came up in my mind. Why did it take so long for ML to get into the one, Internet of Things, and then two, industry? Right? It seems strange.
Again, I think it's because we've done so well with domain understanding, right? You've got people who can look at a time series and go, oh yeah, it's that bolt that's falling off. Right? We've done so well with that because that's all that existed 50 years ago, right? And the competition for being able to maintain these systems and service these systems wasn't really there until recently. And the data was kind of analog, right? It wasn't just, let me look at a screen and look at this chart that was made in D3 and go, there's a bolt falling off. This was, let me look at the gauge and tap it and go into the factory and listen and go, oh yeah, it's that thing over there. So we've done extremely well with domain expertise, right? In a way that, Amazon was lucky because it came up in the world where web scale was just sort of assumed. You can imagine in the early days of Amazon, making recommendation engines was a bunch of people sitting around in a room saying, I think that person would really like this, right? That doesn't scale very well in the consumer world. But when you've got 50 turbines and you've got one person that's their 50 children and they visit them every day, you can do quite well. That's one answer. The other answer also is physics, right? So these are physical objects for which, when it's really important, we have supercomputing models, finite element analysis models of these things, and we can see what's going to happen to them if you put them in different environments. And so we've been able to get away with it for so long because we've done pretty well. And now the question is, can we do even better?
So, what would you give as advice to a younger Josh Bloom, maybe 20 years ago, in terms of starting off just in his career?
Well, I think what's important is to recognize that it's important to understand what is cutting edge, to be able to work with people that know more than you, to be able to learn from them. But you need to develop your own opinions and your own instincts about what is going to be important in the future. What happened for me in the academic world is I got a sense that doing machine learning on time series data was going to be interesting and important. And what I would have I should have told myself is to go more all in on that, and get as deep as I could on that as quickly as I could on that. And so I think that's something you want. Most people need to hear is that if there's an aspect that you're not hearing a lot of people talk about, it doesn't mean that it's not interesting and it's not important for you to spend time on it. Especially if you start building up enough domain knowledge to realize that that is a white space. And in terms of making an impact in the academic world and in industry, following your instincts and knows on that is a good thing to do. Now, that can actually also be dangerous. If you start following your instincts because you saw, you read something in Hemispheres magazine, and you're like, that's a cool term, I'm going to do that. That might not be a good reason to do it. But if you get enough domain expertise to recognize that there's something missing, it's worth figuring out, is there something there that I could actually have a big impact if I solve?
That's an awesome answer.
That's great advice.
Cool. Where should people go to learn more about GE? And
so ge.com/digital has a lot of great blog posts, sort of keeping everyone up to date on our view on industrial Internet of Things, on the Predix platform that we're selling, and how AI is starting to get infused into the products that GE uses and builds.
Excellent. Josh, thank you so much for the time today.
Thanks, guys. Thanks for having me.